Hello everyone, welcome to my YouTube channel. So today we'll be solving D1 Candy Party question, that is D1 question of Codeforces round 896. Okay, so pause for the moment, read the question, and then we can continue. Okay, so cool. What the question is saying? Question is saying that there will be n party, there will be a party, and there will be n people, and each people will have some amount of candies. Let's say A of icon. Okay. Now what we need to do, we can have one operation or basically one operation all where we will be giving candies to each other persons. So constraint is we can always choose only one person to give candy, and we can receive candy from only one person. Okay. So what it's exactly saying is, so there are p people, let's say. So any one people can give to any one of the other people. Okay, it's not like that you he can give to two other people. He can give candies to only one people. So at the end, what will happen is, so basically, let's say I have one, two, three, four, I have six people. So I am saying that one can give candy to only one other people. So let's say it give to two, two can give to, let's say, four, three give to five. It's not going to happen that four is also going to give five, because five can receive candies from only one person. Okay, so this is a wrong state. So you'll soon realize that that means each person can receive candy only from one person, and so can give the candy to only one person. Okay, so I hope this will be clear. Now coming back to the question. Now what question is saying that, yeah, and one more thing, that whenever a person is giving candy to another person, he can give only 2 to the power x candies. X can be anything, okay? As long as he have enough candies to give 2 to the power x candies. It's like, let's say if he has 10 candies, then he can't give 16 candies, right? So here x will be 4, like 2 to the power 4 is 16. So as long as he met the criteria that he have enough candies, so like if he has 10 candies, he can give 8 candies. So here x will be 3, like 2 to the power 3 candies he can give at max. Okay. Now there is one guy, Daniel, who likes fairness, and he wants that, yeah, that's the condition we already discussed, that each person will receive candies from exactly one person. Okay. And second is Tom likes average. So what he wants, that every person have equal number of candies at the end after all the swaps. So after all the swaps, that means there will be n swaps basically. So after n swaps, he wants everyone to have equal number of candies. Okay. I hope question will be clear. Let's move to the solution, or I would say intuition part, how we can solve this. So what question is saying that, wait, let me just erase it. Okay. So question is saying that, let's say there's a person A, B, C, D, let's something like this. Now A can receive 2 to the power, A can give 2 to the power x candies to someone else. Okay, let's say anybody, let's just see. And we also know that at the end A will be receiving candies from someone else. So let's say he is receiving from D. So we know that D can also keep candies only in the power of X. So let's say he was giving to the power Y candies. So A will be receiving to the power Y candies. Okay. So what we can say, that each person P will receive will, let's say, receive to the power Y candies. Okay. And is giving to the power X candies. Okay. So what we are saying, that each person P will be receiving 2 to the power Y candies and giving 2 to the power x candy. So if he has initially C candies, so what will happen at the end, that he will have 2 to the C plus 2 to the power y minus 2 to the power x candies in total. Okay, that's one thing. Now, what second thing from the question is, we know that each person will have equal number of candies. Okay, so let's say there are total number of candies T. Okay, total candies is equals to T. Then we know that if there are n person, then each person have candies T upon n. Now if t is not divisible by n, that is modulo of upon n is not equal to 0, that means t is not divisible by n, that means we cannot split in such a manner that each person gets t by n candies. So in that scenario we don't have any answer possible and we can simply return no. Yeah, one more thing I forgot to mention, that in question we need to return yes or no if it is possible to split the candies in such a manner that at the end everyone have equal candies, and the other condition is that everyone gave the candies in form of 2 to the power x. So if that those conditions are satisfied, then we have to return yes, else we have to return no. Okay. So the very first thing is, if sum of candies or total candies is not divisible by n, then we cannot have an answer and we can simply return no. Now, let's say that if t is divisible by n and that is equivalent to m. So now what we know, that each person p, for each person p we have m candies. We have m candies. Okay. Now let's say initially p had c candies. We had C candies, and finally it is transforming to M candies. And we know that he can have only two operations. Basically, he can receive from someone 2 to the power Y candies and he can donate someone 2 to the power X candies. Okay. So, and this should be equal to M. Okay. So now what we can do is, let's say we can have a table, like, and also one more thing, that we know that the maximum amount of candies can go to 10 to the power 9, which is less than equal to 2 to the power 31. Okay. So what we know is, if if we know what is the current candies he have and what is the candies we need to make, the difference would be d equals to, we can write that absolute value of c minus m. We are using absolute value, that maybe we, what we can say is that if he was having less candies, then he can receive 2 to the power y, sorry, then yeah, he will be receiving 2 to the power y candies and subtracting a smaller value 2 to the power x candies. But if we have more candies, then he will be giving a smaller number, that is 2 to the power x will be larger and 2 to the power y will be smaller. So we just need to find two values x and y such that the difference should be equal to 2 to the power y minus 2 to the power x. In this scenario, what we can say is, he is borrowing 2 to the power y candies and subtracting 2 to the power x candies. So let's say here, if d is equals to, let's say, what we can say, let's say if 2 to the power is 16 and this is 8. So let's say if we have d equals to 8, then we can have 2 to the power 4 minus 2 to the power 3, that will be equivalent to 8, sorry, not 18, it will be equivalent to 8. Okay. So in this scenario, what we can say is, he will be receiving 2 to the power 4 candies and he will be giving 2 to the power 3 candies. So what we can do is, we can have a count map or frequency map, where what we can do is, frequency of 4 will be increased to 1, initially it will be 0, and frequency of 3 will be decreased, sorry, yeah, we can go either way. We can subtract while giving, or while we can subtract while receiving. So let's say, if he is receiving, we are increasing the count by 1, and if he is subtracting giving, then we are decreasing the count by 1. So we can have something like this. So at the end what we have is, for every x and y, for every x, or for every y, that is, and we know that x and y will range from 1 to 31, because at max 10 to the power 9 we have 2 to the power 31 will be greater than equal to 10 to the power 9. So in worst scenario we'll have 10 to the power, sorry, 31 values to take care of, and we'll have count for each. Let's say we know that count for 1 is 0, or count of 2 is 2. Then count of 2 is 2 means that we will be receiving 2 to the power 2 candies two times. Okay. So when, if we will be giving 2 to the power 2 candies, then we'll subtract the count by 2, count of 2 by 1. Okay. So whenever we will be giving the power any candies, then we will increase the count of its power by 1, and whenever we will be decreasing the candies, sorry, whenever we will be giving out the candies, will decrease the count of power. Okay, I hope this one will be clear. Now there is one more scenario. So in some cases, let's say difference is directly equals to 8 or like 16 or simply 32 or any two power. So in that scenario, what happened is, let's say A was already having 32 candies, or let's not 32, let's to be better, let's say A was having 11 candies and M is R3. Remember, ammo was the total number of candies a person can have, or the maximum number of candies a person can have if we want everyone to have equal candies. Okay. So now let's say A was 11. Then in this scenario, we can see that he just needs to donate 8 candies. Okay. So what we can do is, if if he simply denoted 8 candies to someone, let's say if this person is 3 and this is B, which have 3 candies. Now, if we can see that he only needs 8 candies and he can donate 8 candies, but we cannot have D such that 2 to the power y minus 2 to the power x is equals to 8, such that 2 to the power y should be valid. Like, I mean, there is one possible solution that 16 minus 8 would be 8, but we don't have enough candies, 16. We don't have 16 candies, so we cannot give 16 candies. So, but what we can do is, we can give 9 candies to 3 B, and B can return one more candies to us. Okay, so in this scenario, what we are saying is, the whatever the requirement will be just giving one more candy, and then we'll be getting back few candies. Okay, so we also need to take care of, sometimes this D can directly be 2 to the power y. In that case, we can have one hypothetical character or hypothetical power minus 1, and we will increase or decrease the count. Okay, if it needs 2 to the power y candies, we will increase the count by plus 1. If it is given to the power y candies, so like in this case, like for B, we are taking out we are receiving 2 to the power y candies, so we'll be decrease the count by minus 1. Okay, I hope this will be clear. So at the end, what we'll have map something like this: minus 1, 1, 2, 3, up to 31. And for this each scenario, we'll have count. Okay. Now, whenever we'll be giving out 2 to the power 1 candies, we'll be increasing the count of 1 by 1. Okay. And if we are taking out, then we'll be decreasing the count. So for each time when we will be increasing the count, and when we are receiving, we are decreasing the count, then overall this value should be 0. In case if any value is not equal to 0, that means we are giving that power. Let's say if 2 to the power 3 count is not equal to, is equals to 1. Let's say equals to 1, that is not equals to, sorry, uh, second. So what I'm saying is equals to 1, that is not equals to 0. That means we are giving 2 to the power 3 candies more times than than someone actually is receiving. I mean, that is, let's say if A, B, and C, this is also giving 2 to the power 3 candies. This is also giving 2 to the power 3 candies, and he is receiving only one time 2 to the power 3 candies. That C is receiving basically. So that means we are giving out 2 times but receiving only one times. That means we cannot have this kind of distribution. Okay. So if any times that is not equal to my not equal to 0, in that case that is a false solution, that is not possible. Now sometimes it may happen that D itself cannot be represented as 2 to the power y minus 2 to the power x. Okay, so in that scenario, because let's say if D equals to 7, then we cannot write any power of y in, like, any power of 2 minus any power of 2 equals to 7. So in this scenario also our answer is not possible. Okay. So finally what we have, first of all, what we can do is, if total candies is not divisible by n, is not equal to 0, that means we cannot have our answer, and we can simply return no. Okay. Now second thing, let's say if it is divisible, then if m we have is tc upon n. Okay. Now for each candies, we can have 2 to the power y candies it is giving out. So we'll be increasing the 2 to the power y and decreasing. First of all, what we'll do, we will just calculate difference. The difference will be abs of m minus c. C will be the candies already a have, Okay, then we will be decreasing and increasing the count. We'll be decreasing the count for giving out the candies and increase the count, sorry, increase the count for giving out the candies and decrease the count for receiving out. We can go either way, we can decrease anyone, but we have to follow just one pattern. Either we decrease for every time we decrease, or every time increase for one particular operation. Okay, so now, and then we will check if any at any time d cannot be expressed as 2 ka power x, or let's say 2 ka power y minus 2 ka power x. But there is one particular scenario is if d is equal to 2 to the power x, then we can have one hypothetical number is, let's say, 2 to the power minus 1, or we don't even need to do that. We can always represent 2 to the power y minus 2 to the power x minus 2 to the power y. So x here, y here, we are talking in this fashion. Okay. So if it is not just expressible as a form of this, then we can have no answer and we can simply return 0. Now, and at the end, if in our table, if the count of each number is not equal to 0, that means we are either taking out more candies or we are receiving more candies. So we cannot have answer and we can return 0. Else in the end, we can return yes if all the condition is satisfied. Okay, we can go and look into the code once. So as we need 2 ka power, we need every power of 2. So what we have done is we have already stored power of 2 in a vector, and we know that 10 to the power 9 is at max 2 to the power 31. So we have made a vector of size 32. Okay, so that we can store 2 to the power 31. Now for each candies, first of all, we have taken the input, we calculated the sum and check if sum is divisible by n or not. If not, then we can simply print no and we can return. Else, what we can do is we can have m that is equal to sum divided by n, and now we can maintain a map just to keep a counter of x and y. That is how much 2 to the power x we are giving and how much we are receiving. If first we calculated the difference, if difference is 0, then we don't need to do or worry anything, because we can always write it 2 to the power x. We can increase the count and increase the count, that will eventually result in the same thing. So we don't need to worry about that. We can simply continue. Now we have written x equals to minus 2. It will be acting as flag that if we have found any power of d, okay, if we have found any power of d such that we don't need to you know like we have kept x to equal to minus 2 such that if d cannot be expressed in the form of 2 to the power y minus 2 to the power x, then we can simply return no. So first of all, we have checked if 2 can directly represent the power. In that case, we can simply increment, decrement, minus, we can keep y and then we can simply increment, decrement the value of x and y depending on the condition. If, yeah, so or else it can be expressed as the difference of the powers of two different powers of 2. Okay, that will also be fine. Now, if x equals to minus 2, that means we cannot express directly as a power of 2 or neither the difference of two different powers of 2. Okay, different, because we have already excluded the case of 0. Okay, so if x equals to minus 2, that means whatever the difference d was cannot be expressed in terms of difference of power of 2. So we can simply see out no and return. Else, if the difference was positive, that means if c is greater than m, that means we are giving out x candies because d was 2 to the power x minus 2 to the power y here. Okay, contrary to the explanation, there we have 2 to the power y minus 2 to the power x. Here we have 2 to the power x minus 2 to the power y basically. So we will increase the count of x and decrease the count of y, and if it's not the case, then we will decrease the count of x and increase the count of y. And finally, for each of the value, we must have 2 to the power, sorry, count of every power of x equals to 0. And if it's not, then we can simply return 0. Sorry, we can simply print no and we can return from there. And at the end, if everything satisfies well, we can print yes. Okay. So let me try submitting this solution. So let's submit this solution. This was easy version of Candy Party. Let's submit the solution and wait. Okay, so this will be an AC solution. Let's wait for, yeah. It got easy. So let me know if you have any doubts in the comment section. I'll be happy to help out. Thank you guys. See you in the next video.